All the lectures in this series on QFT a la Weinberg so far have been concerned with one central theme, and that is the application of symmetry methods to quantum mechanics. Of course, we have focused on one particular symmetry transformation, Poisson transformations, but most of what we have talked about can be generalized to other symmetry transformations as well. And the major tool that we have used in all these lectures is a theorem due to Wigner called the symmetry representation theorem. Let me remind you what the theorem is. The theorem essentially says that any symmetry transformation can be represented on the Hilbert space of physical states by an operator which is either linear and unitary or antilinear and antiunitary. Note that we have very deliberately actually said can be represented, not must be represented. You can always find an operator which represents the action of a symmetry transformation with the condition that that operator is either linear and unitary or antilinear and antiunitary. Now let me remind you of exactly what a symmetry transformation is for this purpose. As far as we are concerned, a symmetry transformation T transforms physical states. That means at a quantum mechanical level, they act on rays and not really on vectors. And when they act on rays, their effect is to preserve the transition probabilities. In other words, if the vector psi1 belongs to a ray R1 and the vector psi2 belongs to a ray R2, then any vector psi1 prime which belongs to TR1 and psi2 prime which belongs to TR2 must satisfy the following. The transition probability between psi1 and psi2, which is the inner product of psi1 psi2's modulus squared, must equal the transition probability between psi1 prime and psi2 prime. That is, mod square of psi1 prime comma psi2 prime has to be equal to mod square of psi1 comma psi2. What we are essentially saying here is, at least in the context of the Poisson transformation, two different inertial observers would very well ascribe different state vectors to describe the same physical state. However, the probability of a particular system transitioning from one state to another will be quite independent of who is observing it. So these transition probabilities must stay the same before and after the transformation. Note that psi1 prime is any vector in the transformed ray TR1, and the same goes for psi2 prime. And let me just remind you that a ray is what we are using here simply because the connection between the vectors on Hilbert space and physical states is not 1-to-1, it's actually infinitely many to 1. If you collect together all vectors which differ just by a phase factor, they have the same physics and they together form the ray. So a ray essentially is a generalization to complex vector spaces of the basic idea that instead of considering one vector in ordinary, say, 2D or 3D space, you consider the whole bunch of vectors which are multiple of that, which means you take a line which goes to the origin. That's where the name ray comes from. Notice that when you're talking about a particular symmetry transformation on physical states, you're not really talking about what happens to a particular vector in Hilbert space when the transformation takes place. At least that's not your initial starting point. Your starting point is that you have a physical state which transforms into another physical state, which means you're starting from a ray, let's say curly R1, and then you're going after the transformation to another ray, TR1. So, when you're trying to talk in terms of the action of these transformations on vectors, there is a lot of ambiguity here, in the sense that instead of using the vector psi1 from the ray R1, you could have used psi1 times any phase factor, which also belongs to the ray R1. And that, of course, goes not only for psi1, it goes for psi2, psi1 prime, and psi2 prime as well. So when you are talking about a specific operator which acts on the vectors on the Hilbert space and implements the symmetry transformation, you have this ambiguity to deal with. In fact, it is this ambiguity which you can use to your advantage to bestow on your operators certain advantageous properties. And that is exactly what we are going to do to show that you can always choose these phases in such a way that you are going to end up with either a linear and unitary or an antilinear and antiunitary operator. In addition to this demand, we make another one, which is simply the fact that the inverse of a symmetry transformation must exist, and not only must it exist, it also must satisfy the very same property, that is, it must also preserve transition probabilities. We will show that based on just these two demands, we can always construct operators which implement these transformations by acting on vectors, and those operators will have the properties that we have just mentioned. So, basically the proof of our theorem is by construction. We are going to construct these operators. In order to do this, we will begin with a complete orthonormal set of state vectors, which we are calling psi k. Each psi k belongs to a ray Rk. And because they are a complete orthonormal set, we have this condition psi k, psi l's inner product is delta kl. This normalization condition still leaves us with the freedom to use our states to be any states in the rays Rk, because if instead of taking psi k, you had taken, say, e to the I phi times psi k, which is another vector in the same ray, then the inner product of psi k with psi l, where k is not equal to l, would have been simply multiplied by e to the minus I phi. Remember, the inner product is antilinear in the first factor. That is why e to the power minus I phi. But since it's 0 to begin with, multiplying it by e to the minus I phi still keeps it 0. The only case where the phase factor could have made a difference is when the right hand side is actually non-zero, which is when k is equal to l. But if k is equal to l and you have replaced psi k by e to the I phi psi k, then you basically have the inner product of e to the power I phi psi k with e to the I phi psi k, and because of the linearity in the second factor and antilinearity in the first factor, the two e to the power I phi's cancel each other out, and you are again back to 1. So this particular condition, the orthonormality condition, the inner product of psi k comma psi l equals delta kl, will stay true no matter which vector you choose from the respective rays. Now let's ask what happens when transformation T acts on our system. Each and every one of the rays change. So R1 becomes TR1, R2 becomes TR2, and so on. Now let us consider psi k prime to be any arbitrarily chosen vector in the transformed ray TRk. Remember, Rk is a ray which contains psi k. After the transformation, you have a new ray TRk, and psi k prime is a member of that. Of course, this is not only for the kth ray. This is a statement which I have made for each and every one of the rays. So in particular, if you take psi k prime and psi l prime, form the inner product and take the modulus of that, you must get the same modulus as the inner product of psi k and psi l. Namely, you must get delta kl. So just like the original vectors that you started out with, the psi k's formed an orthonormal set, these resulting vectors after the transformation will also form an orthonormal set. Now, there's a bit of a catch here in the sense that all we have shown is that the magnitude of inner product of psi k prime with psi l prime is delta kl. In order to claim orthonormality, I should really show that the inner product of psi k prime with psi l prime without the magnitude is actually delta kl. But that's very easy to show, because the only case that will actually give us a non-zero result is the case when k is equal to l, and there you're considering the inner product psi k prime comma psi k prime, and our condition is telling us that the magnitude of this inner product has to be 1. However, since psi k prime's inner product with itself has to be, by the very basic property of the inner product, a real number, indeed has to be a positive number, then its magnitude being 1 simply must imply that it has to be 1. So psi k prime, psi l prime's inner product has to be 0 whenever k is not equal to L and has to be 1 whenever k is equal to L. In other words, psi k prime, psi l prime's inner product has to be delta kl, and the new prime psi's also form an orthonormal set. Now, apart from orthonormality, I had made a very important demand on our original set of vectors psi 1, psi 2, psi 3, etc. And that was that they form a complete set. Now, my claim is that this property is also there in this new transformed set of vectors. If you take psi k primes, they also form a complete set. Now, assume to the contrary, that they are not complete. This is the way we are going to prove this result by contradiction. So, if this set is not complete, then there must exist a vector psi prime which is orthogonal to all the psi k primes. In other words, psi prime comma psi k prime, the inner product has to vanish for all k. Now, this is where our demand about the existence of the inverse transformation comes in handy. We had a transformation which was taking us from the psi's to the psi primes, but the inverse transformation of that, acting on R prime, the ray which contains psi prime, in other words T inverse R prime, will contain vectors, and a typical one of them I am writing psi double prime, and what that has to obey is the following. If you take the inner product of psi k with psi double prime and square the modulus of that, you must get the modulus square of psi k prime and psi prime. Basically, we are just using the fact that T inverse has the same transition probability preserving nature. But since psi k prime comma psi prime's modulus square is 0 for all k by assumption, this means that our vector psi double prime must be orthogonal to all the psi k's. And since the ray containing psi double prime will give you the ray containing psi prime when you apply to your net, it stands to reason that psi double prime cannot be 0. But that is an impossibility. Since we have already assumed that the set psi 1, psi 2, that is the original psi k set, is a complete set, any vector which is orthogonal to all of them must be the null vector. So we have a contradiction here. And because of this contradiction, our claim is proven. That is, our new set psi prime k's form a complete set of vectors. So at this stage, starting from an orthonormal complete set psi k, we have landed up into a new orthonormal complete set psi prime k. Now, what must be clear to all of you is that if we think of the new vectors psi prime as a result of some operator u acting on the psi's, that is, psi prime k is an operator u acting on psi k, then if this operator happened to be unitary or anti-unitary, what you would get is psi k prime comma psi l prime's, this inner product, would have to be either equal to psi k comma psi l in the unitary case, or its complex conjugate in the anti-unitary case. And in both the cases, you would have ended up with the orthogonality relation psi k prime psi l prime inner product is delta kl. So, if these new vectors had been obtained by the action of an unitary or an anti-unitary operator on the original vectors, then whatever we have found so far would have automatically occurred. What we want to show here is that if you turn the argument around and you say that you started with an orthonormal set and you must get an orthonormal set, then it is always possible to choose an operator to carry out this transformation, and this operator can always be chosen to be either linear unitary or antilinear antiunitary. Note that the reason why a proof of this statement is still a long way away is the huge amount of flexibility you have in choosing the psi prime case. So far all we have said is psi prime k is a vector which belongs to the transformed ray TRK. that leaves for a huge amount of ambiguity as far as the overall phase of psi prime k is concerned. And what we will have to do is exploit this ambiguity in the phase in our favor to end up with an operator with the desired properties. So our next task in this construction of the operator U is to set up a phase convention for the psi prime case. And in order to do that, what we are going to do is we are going to take each k in succession and define a new state vector. Okay, I said each k in succession, but what we will do is we will arbitrarily choose one of these k's out. Let's say k equal to 1. So we will treat psi 1 differently. But for all the other k's, k not equal to 1, we will define a new vector called epsilon k, which is simply a superposition of psi 1 with psi k, a 50-50 superposition with coefficients 1 by root 2. Now, these new vectors epsilon k will of course belong to some ray or the other, and I am calling the ray which contains epsilon k the S key. The question now would be to figure out what happens to this ray Sk under the transformation T. If we consider any vector epsilon prime k which belongs to Tsk, then you can definitely expand this vector in the psi prime case. Remember, we have already shown the psi prime case form a complete set. So every vector in the space, in particular epsilon prime k, can be expanded in terms of psi prime case. So in particular what we can write is epsilon prime k equals some linear combination with coefficient ckl of psi prime l. But now comes the demand about the transition probabilities staying the same. Since epsilon prime k and psi prime l must have an inner product whose magnitude matches the inner product of epsilon k and psi l. Once again, this is a symmetry transformation. Can very well change vectors, can also change the inner product of vectors, but cannot change the magnitude of the inner product, which is related to the transition probability. And this immediately tells us that in the expansion that we have, epsilon prime k equals sum over L ckl psi prime l, almost each one of the coefficients ckl vanish. In fact, if L is not equal to 1 or equal to k, then this magnitude of ckl has to be 0, which means ckl has to be 0. The only non-zero coefficients can be ckk and ck1, and they must have magnitudes which are equal to 1 by root 2 each. So all we have used is that ckk, which is just the inner product of epsilon prime k with psi prime k, must have the same magnitude as the inner product of epsilon k with psi k, which we know is 1 by root 2. And the same goes for ck1 as well as ckl, where L is neither 1 nor k. So rather than a sum over all the psi prime l's, this epsilon prime k can be written down as a superposition of just psi prime 1 and psi prime k with coefficients ck1 and ckk respectively. And what we know so far is that the magnitude of these two coefficients ck1 and ckk have to be 1 by root 2. But so far we have no clue about exactly what ck1 or ckk has to be. As far as the symmetry transformation is concerned, you are fully free to choose psi prime 1, psi prime k, etc. with whatever phases you want. In fact, you are also fully free to choose the phase in epsilon prime k, and therefore the phases in the coefficients are completely arbitrary at this stage. But as I have said before, what we are going to do is make use of this phase ambiguity to actually help us out. Now, each of the k's, psi prime 1 is common, but the other vectors, psi prime k and epsilon prime k, change when you go from one k to another. Now, for each one of the k's, what we are going to do is adjust the phases of epsilon prime k and psi prime k independently, which is what we can definitely do, because remember, so far all we know is that psi prime k is a vector in the ray trk. That's all we know about psi prime k. So I'm fully free to change its phase. Similarly, upsilon prime k is a vector in the transform rate tsk. And once again, I'm fully free to change its phase. So if you change the phase and denote the changed phase versions with a bar on top. So upsilon bar prime k is the I phi 1 times upsilon prime k, and psi bar prime k is the I phi 2 times psi prime k. Then if you substitute this back into the original equation, upsilon bar prime k is the I phi 1 times the right hand side of the original equation. So that's ck1 the I phi 1 psi prime 1 plus ckk the I phi 1 times psi prime k, but psi prime k, remember, is the minus I phi 2 times psi bar prime k. So in terms of the new phase changed vectors, you get upsilon prime k is ck1 the I phi 1 psi prime 1 plus ckk the I phi 1 minus phi 2 psi bar prime k. Now remember, ck1 and ckk could have any arbitrary phase whatsoever, but their magnitudes would have to be 1 by root 2. We can always choose the I phi 1 so that it cancels the phase factor term in ck1. That is, it makes the product completely real. And the same can be done for the other coefficient by choosing phi 2. Remember, phi 1 choice has already been exhausted. If you try to make ck1, it is I phi 1 real. So you cannot change that phase any further, but you can change phi 2, and because you can change phi 2, you can also make the coefficient in front of psi bar prime k completely real. Of course, when these coefficients become completely real, they have to be 1 by root 2. By the way, you could also have chosen minus 1 by root 2 for that case. We are choosing the phases in such a way that the resulting products become plus 1 by root 2 for each. That's just a convention we are following. And if that happens, then we get upsilon bar primed k equals 1 by root 2 times psi prime 1 plus psi bar prime k. Note one very important thing. For each and every k, you are fully free to adjust the phase of upsilon prime k and psi prime k. But you are not going to touch the phase of psi prime 1. Simply because there is only one psi prime 1. You can adjust its phase once, definitely. But you can't do it once for each k. You have to do it once and for all. It is at this stage that our hero, the operator u, makes a partial entry into the scene. What we are going to do is denote these phase adjusted vectors, upsilon prime k and psi prime k with bars on top, by u upsilon k and u psi k respectively. Psi prime 1 is going to be denoted by u psi 1. And once we do that, we at least get a relationship which looks very much like what a linear operator would do. U acting on upsilon k, that is u acting on 1 by root 2 times psi 1 plus psi k, will give you 1 by root 2 times psi prime 1 and psi bar prime k, which are u psi 1 and u psi k respectively. So this looks very much like the standard behavior of a linear operator. However, note that at this stage we are in no position to claim that u is a linear operator. Firstly, even an antilinear operator would have given you exactly the same result, simply because the coefficient that we have here, the two 1 by root 2s, are both real, so conjugation will not affect them. But more importantly, what we have stated here is just what u does to upsilon k and psi k. Before we can even make a statement about the linearity or otherwise of the operator u, we have to fully define the operator u. That is, we have to say what u does to every vector, not just these special vectors. The reason why I am stressing this is the following. We are so used to using linear operators in quantum mechanics that any operator looks to us as if it's a linear operator by default. So many of the things that we will still have to prove seem like a foregone conclusion to us, but that's really not the case. Right now we do not know what u does to an arbitrary vector. All we know is u acting on psi k gives you psi bar prime k, and u acting on epsilon k gives you epsilon bar prime k. And at least in this limited situation, u acting on 1 by root 2 psi 1 plus psi k does give you 1 by root 2 u psi 1 plus u psi k. What we now have to do is to check whether these extend when we go beyond these special vectors and look at arbitrary vectors. So, what we need to do is take a look at an arbitrary general vector psi. So, psi which is given by sum over k of ck psi k, where ck is just any arbitrary bunch of complex coefficients. Now, psi belongs to some ray r, of course, and what we can do is take a state psi prime which belongs to a transform ray tr, and because the u psi k's are all orthonormal and complete, I can always write psi prime as ck prime times u psi k. Note that at this point I am making no statement whatsoever about linearity or otherwise of the operator u. If the operator u had been linear, then the c prime k's would have to be equal to ck. If the operator u had been antilinear, then the c prime k's would have become ck conjugate by default. But at this stage, we are making no such claim as of now. All we are saying is that u psi k's form a complete orthonormal set, and so any vector psi prime can be expanded in terms of u psi k's. It is exactly the relationship between the new coefficient c prime k and the old coefficient ck that we have to establish at this point. In order to investigate the relationship between the coefficients ck prime and ck, let us fall back upon the vectors u psi k and u epsilon k. The inner product of psi prime with u psi k must have the same magnitude as the inner product between psi and psi k. And that immediately gives us ck prime mod square from the inner product of psi prime u psi k mod squared equals ck mod squared. That's the inner product of psi with psi k mod squared. If you repeat the same thing with u epsilon k, what you get is psi prime u epsilon k mod square equals psi epsilon k mod square, and that gives rise to the equation ck prime plus c1 prime mod square equals ck plus c1 mod square. The first of these two equations, ck prime mod square equal to ck mod square, is true for all k, and the second one is true for k not equal to 1. Remember, epsilon k is defined only for k not equal to 1. We can now divide both of these equations by c1 prime mod square on the left and its equal value c1 mod square on the right to get two new equations which will reveal to us the relationship that we were looking for. The two equations that we get, of course, are ck prime by c1 prime mod square equals ck by c1 mod square, and ck prime by c1 prime plus 1 mod square is equal to ck by c1 plus 1 mod square. Now, just to see what these equations mean, geometrically, we can just draw a simple plot on the Argand diagram that is being shown on the right now. If you denote ck by c1 by z and ck prime by c1 prime by z prime, the first of these two equations simply tell you that z mod square equals z prime mod square. Geometrically, that means both the points z and z prime lie on the same circle centered at the origin. The red dotted circle that you can see on the screen, both z and z prime must lie on that circle. On the other hand, the second equation becomes z plus 1 mod square equals z prime plus 1 mod square, which essentially means that the 2 points z and z prime are both at equal distances from the point minus 1. In other words, they both lie on a circle centered at minus 1. This is the blue dotted circle that you can see on your screen right now. since z and z prime both must lie on this circle, they must be at the intersection points of the two circles. So the two red circles that you can see on your screen are the possible locations for the complex numbers z and z prime. It is obvious from simple geometry that the 2 points are symmetrically placed above the line joining the center of the two circles, which in this case is just the real axis. So these 2 points represent complex conjugates of each other. So there are now 2 possibilities. Either z and z prime are the same point, in which case, of course, z equals z prime, or they are different points which are symmetrically placed above the real axis, which means z prime is the conjugate of z. Weinberg derives this result algebraically. However, I personally prefer this geometric way of arriving at this result. In either case, the result is the following. Either we have ck prime by c1 prime equals ck by c1, which is the z equal to z prime case, or you have ck prime by c1 prime equals the conjugate of ck by c1. Let me remind you that if u had been linear, then ck prime by c1 prime would have been equal to ck by c1 for all k. On the other hand, if u had been antilinear, then ck prime by c1 prime would have been the conjugate of ck by c1 for all k. Now apparently, Wigner in his original proof did not spot that the logic that he is using here is incomplete unless he manages to show that ck prime by c1 prime is either equal to ck by c1 for all k or its complex conjugate for all k. All he did was show this result and proceed to the next step. Weinberg has filled up this gap in the proof, and that is what I am going to describe next. This step, which apparently Wigner missed, is this particular claim whether ck prime by c1 prime is ck by c1 or its conjugate. The same choice has to be made for all k, of course all k not equal to 1. For k equal to 1, both the relations above equals 1 and they are trivially satisfied. So in order to fill up this gap in Wigner's original proof, Weinberg proceeds to prove this result that the choice has to be the same for all k, and for this we again start with assuming the contrary. Let's say there are 2 distinct values for the index, let's say m and n, such that for cm prime by c1 prime you have that equal to cm by c1, whereas cn prime by c1 prime is equal to the conjugate of cn by c1. For this to happen, m is definitely not equal to n, and we are further assuming that both the ratios that are involved here are non-real. After all, if the ratios were real, then there is no difference between the value and its complex conjugate, and then both equations would essentially say the same thing. So our assumption is we do have 2 indices m and n for which this choice differs, and differs in a non-trivial manner because the ratios involved are not real numbers but complex numbers. In order to show that this is a contradiction, we start with a vector phi given by 1 over root 3 psi1 plus psi m plus psi n. This is of course a superposition of all the psi k's, but with a special choice, c1, cm, cn are all equal to 1 by root 3, which are all real numbers of course, and the rest of the coefficients are all 0. So now, since cm by c1 and cn by c1 are both equal to 1, cm prime by c1 prime must be equal to 1, and cn prime by c1 prime must be equal to 1's conjugate, which is also 1. In other words, all the 3 coefficients in u phi must be equal to c1 prime. And thus, any state vector that you can take from the transformed ray, the ray which you get when you transform the ray containing phi, must be of the form alpha over root 3 u phi 1 plus u phi m plus u phi n, where alpha is a pure phase, that is, it has a magnitude of 1. And now we play the same game that we had played earlier, but this time with phi prime. The inner product between phi prime and psi prime must have the same magnitude as the inner product between phi and psi. And that gives rise to this result. 1 plus Cm prime by C1 prime plus Cn prime by C1 prime mod square must be equal to 1 plus Cm by C1 plus Cn by C1 mod square. Of course, what I've done is I've found out the inner product of phi prime comma psi prime mod square and then divided by C1 prime mod square on the left and its equal number C1 mod square on the right. This, of course, is exactly the same as 1 plus Cm by C1 plus Cn star by C1 star mod square equals 1 plus Cm by C1 plus Cn by C1 mod square. Now, if I now call this quantity 1 plus Cm by C1 u and this quantity Cn by C1 v, this equation becomes u plus v's magnitude is the same as u plus v star's magnitude. Now, this can happen under two situations. One, the more obvious one, is where v is real, in which case, of course, both sides are exactly the same. The other case can happen if v and v star are two different points on the complex plane, then minus u, whose distance from v and v star both sides of this equation actually denote, must be equidistant from v and v star, and therefore it must be on the perpendicular bisector of the line joining v with v star. And this means that minus u and hence u must be on the real axis, which of course is a contradiction because we started out with the assumption that neither of the two ratios involved are actually real. So this contradiction forces us to conclude that our original assumption, that is, you do have two different indices m and n, such that Cm prime by C1 prime is equal to Cm by C1 and at the same time Cn prime by C1 prime is equal to Cn by C1's conjugate, is not a valid possibility. In other words, you can either have Ck by C1 equal to Ck prime by C1 prime for all k, or you can have Ck prime by C1 prime equals the conjugate of Ck by C1 for all k. So with this proof, we can finally state that if psi prime equals Ck psi k belongs to a ray R, then any vector in the transformed ray TR must be of the form Ck times u psi k, with either Ck prime by C1 prime equals Ck by C1 for all k, or Ck prime by C1 prime equals Ck by C1's conjugate, again for all k. In addition to this, we have the demand that C1 mod square must be equal to C1 prime mod square. Now, in the former case, that is, when Ck prime by C1 prime equals Ck by C1 for all k, what we can do is choose the phase of psi prime, the overall phase, so that C1 prime equals C1. In the latter case, what we will do is choose C1 prime equals C1 star, and we will end up with one resulting vector in the transformed ray TR and call that resulting vector u psi. Notice that if you couple the relationship Ck prime by C1 prime equals Ck by C1 with the demand that we have just made, C1 prime equals C1, we get Ck prime equals Ck for all k. On the other hand, if you couple Ck prime by C1 prime equals Ck by C1's conjugate with the corresponding demand that C1 prime is the conjugate of C1, we get Ck prime equals Ck star for all k. So, the two cases correspond to either u acting on sum of Ck psi k is equal to sum over k Ck u psi k, or the other possibility, u acting on sum of Ck psi k equals ck star u of psi k. This may have already convinced you that u is either linear or antilinear, but there is a gap in the logic that we still need to fill up. What we have shown is for a given vector in the Hilbert space, this particular vector sum over k ck psi k, u acts either linearly or antilinearly. But there is still a possibility which we haven't ruled out yet. Is it possible for the action of u to be linear for one state vector, say sum over k ak psi k, and antilinear for another state vector, say sum over k bk psi k? In other words, is this a possibility? U acting on sum of ak psi k is sum over k ak u psi k, whereas u acting on sum over k bk psi k is sum over k bk star u psi k. All the things that we have proven so far do not rule out this possibility as of now. But in order that this become a non-trivial statement, we must demand that neither all the AKs nor all the BKs have the same phase. If all the AKs had the same phase, then whether you are using the AKs or their conjugates don't really make a difference, at least don't really make a non-trivial difference, because even if the AKs were all complex but with the same phase, then the conjugates would also be complex but their phases will all be the same. So you can take the overall phase out and the two resulting states, either with AK or AK conjugated, would give you exactly the same result. So you will not be able to distinguish the two cases. So these two results are actually assumed to be different at this stage, and what we need to show is that this is really not a possibility. Now, to show that this is not a possibility, we fall back upon our basic property of any symmetry transformation, that is, it preserves transition probabilities. So, mod squared of bk psi k inner product with al psi l is the same as the mod square of inner products u acting on sum over k bk psi k and u acting on sum over l al psi l. Since u acting on sum over k bk psi k is sum over k bk star u psi k, but for l you don't have a conjugation, this is the equation that you have to obey. Using the fact that the psi k's are orthonormal and so are u psi k's, you immediately see that the left hand side becomes sum over k bk star ak mod square, whereas the right hand side is a modular square of sum over k bk star's conjugate times ak, that is sum over k of bk ak. So it may appear that it is still possible for you to act differently, linearly on sigma k ak psi k and antilinearly on sum over k bk psi k, as long as this particular condition works. To see exactly what this condition implies, let me just break up this term a bit. Of course, the modulus squared of a number is equal to its conjugate times itself, and just by changing dummy index k to L, we can write that as a sum over both k and L of bk star ak times bl al star on the left and sum over k and L bk ak times bl star al star on the right. We now proceed to break these terms apart into the cases where k equals L and for all pairs k not equal to L. It's easy to see that when k is equal to L, both sides give you exactly the same sum, bk mod square ak mod square summed up over k, and you can easily cancel that out. The k not equal to L terms actually give you a non-trivial condition, that is, sum over k not equal to L bk star bl ak al star must be equal to sum over k not equal to L bk bl star ak al star. Ak al star is common to both terms, but the terms involving b's differ. If you bring them all to one side, it's obvious that this thing actually is telling you that the condition that has to be satisfied is for all K and L pairs with K not equal to L, if you sum up this quantity AK AL star times imaginary part of BK star BL, you are going to get 0. We can of course get rid of this condition K not equal to L in this sum over K and L, simply because for the terms where K is equal to L, you have imaginary part of BK star BK, and since BK star BK is a real number, the imaginary part of course vanishes. Now, this condition involves complex numbers, and therefore it looks like this really is two conditions, one for the real part and the other for the imaginary part. Indeed, we can break up the expression above into two pieces, one involving the real part of AL star. The imaginary part of BK star BL is already real, so that doesn't come into the decomposition, plus I times the sum involving imaginary parts of both BK star BL and AKAL star. However, it turns out that the first sum here, the sum over K and L of real part of AKAL star times imaginary part of BK star BL is identically 0, so that doesn't impose any conditions. To see that, all you need to do is interchange the K and L dummy indices, and if you do that, the real part of AKAL star becomes real part of AL AK star, real part of its conjugate, so this does not change under the switch, whereas here you have the imaginary part of BK star BL in the original term, but now you are ending up with the imaginary part of its conjugate, which of course changes sign. So this sum, which must stay the same under a dummy index interchange, actually changes sign, and therefore it must be 0. So we are essentially left with only one condition, and that is sum over K and L, imaginary part of AK star AL times imaginary part of BK star BL equals 0. I switch the order of the A's here simply to make the thing look a bit more symmetric. Now this is the condition then that the coefficients of two wave functions sigma AK psi k and sigma BK psi k must obey in order to allow the operator U to act differently on the two, that is linearly on sigma AK psi k and antilinearly on sigma BK psi k. We will now proceed to show that even if this condition were to hold for particular AKs and BKs, which is of course always possible, you still cannot act differently on the two wave functions. And for this, what we have to do is to introduce a third wave function, sum over k, ck psi k. The coefficients ck for this new wave function must be chosen in such a way that our condition for unequal behavior under U of the two wave functions involved is not satisfied either by the A's and C's or by the C's and B's. That is, while the sum of the imaginary part of AK star AL times imaginary part of BK star BL vanishes for A's and B's, the corresponding sum for A's and C's does not vanish, neither does the corresponding sum for C's and B's. Remember, the vanishing of this particular sum is essential to ensure that the two wave functions behave differently under U. But since you don't have the vanishing in the later two cases, sum over AK psi k and sum over CK psi k must behave the same way under U, and sum over CK psi k and sum over BK psi k must also behave the same way under U. And what that means is sum over AK psi k and sum over BK psi k, despite satisfying our condition, must behave in the same way under U. In other words, all wave functions must behave either linearly or antilinearly under the action of U. This of course means that we have established that U must be either linear because it acts linearly on all vectors, or antilinear because it acts antilinearly on all vectors. Now at this stage, you may very well have a concern, and a very valid one at that, which is the following. Is it at all possible to find a set of coefficients ck such that the expression above will not vanish for a's and c's or c's and b's, even if it does vanish for a's and b's. So let me just give you the argument that you can always find such c's. Note that the condition that we have stated is trivially satisfied if all the a's had the same phase or all the b's had the same phase. But that is the case we are not interested in. Because, as we have already explained earlier, under such a situation, you cannot really distinguish between whether an operator is acting linearly or antilinearly. And it is a good thing that that is the case that we are not interested in, because that is the one case where it would be impossible for us to find a set of C's which satisfy both the conditions that we want. Simply because if all the A's had the same phase, imaginary part of AK star AL would vanish for all pairs. The sum over K and L of imaginary part of AK star AL times imaginary part of CK star CL would end up being 0. And a similar thing can be said about the situation where all the B's had the same phase. Thankfully, as I said, that's the case we don't really have to worry about. So we are considering situations where at least for some pairs K and L, AK star AL is complex, and for some BK star BL are complex. Now, if we can find a particular pair of indices K and L such that both AK star AL and BK star BL are complex numbers, then it's very easy to find a set of C's for which our demand is met. All we have to do is choose the Ci's to vanish unless I is equal to K or L, and choose CK and CL to have different phases so that the imaginary part of CK star CL does not vanish. That will immediately imply that there is only one term in the sum involving A's and C's and one term in the sum involving B's and C's, and that term is not 0. Now things become slightly more complicated if for all pairs for which imaginary part of AK star AL is not 0, you have imaginary part of BK star BL vanishing and vice versa, so that the condition for A's and B's is satisfied. To show that you can still find C's which meet our demand in such a case is slightly more involved, but it just involves using a pair of indices K and L for which AK star AL is complex, and another pair of indices M and N for which BM star BN is complex, and then choose C's which vanish except when the index is K, L, M or N, and just set their phases distinct so that none of the imaginary parts vanish. It should be very easy to convince yourself that even in that case we should be able to find out C's which will satisfy our demand. To wrap up now, we have two cases. One in which for all psi of the form sum over K CK psi K, U psi is of the form sum over K CK U psi K. Now, it's sort of obvious that such an operator is linear, but to show that explicitly, all we do is take two wave functions psi A and psi B with coefficients AK and BK respectively, and apply U on alpha psi A plus beta psi B, where alpha and beta are two numbers. Of course, alpha psi A plus beta psi B can be expanded in terms of psi K, and the expansion is trivial. It's sum over K, alpha AK plus beta BK psi K. So, in this case, U is acting on sigma K CK psi K, where CKs are alpha AK plus beta BK. But according to what we have just proven, the CKs just come out and U gets to act on psi K in the sum, and that's the same as alpha times sum over K AK U psi K plus beta times sum over K BK U psi K, which is alpha times U psi A plus beta times U psi B. That, of course, is what we mean when we say U is a linear operator. Now, with U linear, it's easy to see that U psi A, U psi B is inner product, which is of course going to be sum over K and L, AK star BL times the inner product of U psi K, U psi L, will simply reduce to AK star BK sum, because U psi K, U psi L, remember, has an inner product which is delta KL, and that means U psi A, U psi B's inner product is the same as psi A, psi B inner product, And this implies that our U is unitary. So in the first case, U is linear and unitary. Now what about the second case? The second case proceeds exactly in the same manner. Here the demand is, for all psi belonging to Ck psi k, U psi is Ck star U psi k. It's rather trivial to show that when U acts on a linear combination of two wave functions psi a, psi b, with coefficients alpha and beta, the result turns out to be alpha star U psi a plus beta star U psi b. That A there is a typo, it should be B. And hence U is antilinear. What about unitarity? In order to form the inner product of U psi a and U psi b, we just use the fact that U psi a is sum over k, ak star U psi k, whereas U psi b is sum over L bl star U psi l. So this is sum over both k and L ak bl star times U psi k U psi l. Once again, use the fact that U psi k U psi l is delta kl to get sum over k ak bk star, not ak star bk, but ak bk star. So this is not psi a comma psi b, the inner product, but its conjugate. Hence, we have established that this U is anti-unitary. Let me sum up what we have done so far. We have started with the demand that we have a transformation between rays which preserve transition probabilities. What we have then done is start with a complete orthonormal basis and then transformed the rays containing those basis vectors, picked vectors with phases chosen specially from those transformed rays to form the U psi k's, and then shown that this U psi k is a complete orthonormal set. And finally, we have gone on to show that if you were to take any wave function belonging to a ray, transform that ray according to our symmetry transformation, the demand that transition probabilities do not change will end up ensuring that this operator U must be either linear unitary or antilinear antiunitary. Thus, we have established Wigner's symmetry representation theorem. This brings us to the end of a rather long journey. I misspoke. It is only the end of one small leg of this journey. In all the videos of this series I have made so far, I have only been able to discuss one chapter of Weinberg's book, the second chapter of volume 1. Those of you who have access to the book may realize that there is a small section I have omitted, Appendix C to this chapter. There, Weinberg discusses some exotic possibilities for the representation of discrete transformations, space inversion, and time reversal. Since these representations, though logically possible, do not show up in the real world, I have decided not to talk about them. In any case, 30 videos does seem too long for one chapter. It is possible that I may have explained things in way too much more detail than is really necessary, but since most of these videos have been made so that I can remember them later on, I think the effort was well worth it. Now, many of you may be wondering, where is the field theory in all of this? And you would be right. So far, we have not really touched upon quantum field theory at all. All that we have discussed so far is the use of symmetry methods in quantum mechanics with a special goal towards understanding the way in which Poincare transformations are implemented in quantum mechanics. We have not yet come to a stage where we can discuss why the implementation of a relativistic structure within quantum mechanics forces us to use fields. One reason why Weinberg's book is different from other textbooks on quantum field theory is that here the aim is not to be able to get to a stage fast where you can do calculations with real life problems or things which look like real life problems. The aim essentially is to look at the structure of quantum field theory as a whole. So whereas other textbooks would discuss things like scalar field theory to begin with and then talk about Dirac fields perhaps, bringing in actual calculational tools as soon as possible, Weinberg chooses to defer them to a later stage. He rather introduces all possible fields which are consistent with relativity in one go. And this study that we have carried out in this particular chapter, the possible representations of the Poincare group in a quantum mechanical scenario, will come in very handy for that. As I have perhaps stressed before, if you are really studying quantum field theory for the first time, you may be better off studying it from some of the other excellent texts around which discuss quantum field theory in a more direct manner, but there the overall structure of the theory is not really illustrated the way it is in Weinberg. Weinberg would be wonderful to come back to after you already have grasped some understanding of the theory from other books, or as the case may be, practicing it directly in your research. In any case, the discussions we have had about symmetry methods in quantum mechanics can actually be used even beyond quantum field theory. It is useful wherever you're going to use quantum mechanics. The next chapter is on scattering primarily, and that too is of general use beyond quantum field theory. So I hope that it will be useful even if you are not going to study quantum field theory in the long run. So I will see you again with the third chapter of Weinberg at a later date.